Good morning, everyone. Today, I'll be presenting a work on improving the robustness of device-independent QKD. This is joint work with the Center for Quantum Technologies in Singapore, as well as the Leibniz University, Hannover. I'll begin with a quick background introduction to device-independent QKD, and then I'll explain the proposal that we have in this work in order to improve its robustness against noise. I'll also briefly explain the method that we use in order to compute the key rate for this proposed protocol. I will then proceed to describe the results of our work, and in particular, I will explain what its implications are for the existing Bell test experiments. Importantly, our work leads to several important follow-up questions, which we are now actively pursuing, and I will proceed to explain. There are also a few other generalizations that I will describe, which may be also of separate interest. So to begin with, the basic scenario for device-independent cryptography is a Bell test scenario. Alice and Bob have a pair of quantum devices which share a certain state between them, and the adversary Eve is given the purification of the state. During the protocol, Alice and Bob will interact classically with the devices, so they only send in classical inputs and they receive classical outputs from the devices. If we assume the devices are modeled by quantum theory, then this process of supplying inputs and getting outputs can be described using measurement operators, as we denote in the boxes here. With a little bit of care, it's possible to argue that we can assume the measurements are all projective, so we have chosen to denote them using P in these boxes. For the purpose of this work, we will focus on situations where the Bell inequality being measured is the CHSH inequality. So this is the one that was studied in the original ETHZ 91 protocol, for instance. And the underlying idea is essentially that if the observed CHSH value is larger than the classical value of 2, then we can conclude that the state shared by Alice and Bob is entangled. So there is at least some potential for generating a secret key, even though this is not a completely sufficient condition. But the important point about this conclusion, and what is interesting about the ETHZ 91 protocol, for instance, is that this conclusion can be drawn even if you do not know what measurements the devices are performing, or even if you don't know what dimensions the systems are. So this leads to the notion of device-independent cryptography, where you don't necessarily need to trust that the measurement devices are performing the intended measurements. You just need to make some fairly minimal assumptions regarding the device behavior. The challenge facing device-independent cryptography, however, is that we need to know how robust it is when there is noise in the system. And one very important quantity in that case to consider is what is the key rate of the DIQKD protocol. Many proposals for DIQKD currently are focused on situations where they only have a single pair of measurements for key generation, which we denote as A0 and B0 on this slide here. And for simplicity, we'll only focus on the situation where the protocols use one-way communication, and as mentioned, we'll only look at those that are based on the CHSH inequality. So for these situations, the asymptotic key rate is given by the expression in the box here, known as the Devitat-Winter bound, at least for the situation of IID attacks. However, this expression was essentially extended to coherent attacks in a fairly recent work. So in order to use this expression for the key rate, we don't necessarily need to restrict to the IID situation. It also applies in the coherent attack situation for the DIQKD. Since many existing security proofs for the DIQKD are based in this setting, I'll roughly refer to this as the standard protocol. But if we think back to earlier proposals for QKD, we might remember that the situation there might have been slightly different. It was quite common to have protocols where the honest parties pick their measurement choices uniformly at random, and then they sift out the rounds where they measured in the matching basis. So in that case, the key rate is essentially the average of the key rates in the cases where the bases match. So it's the expression written here. Of course, in more generality, you could consider situations where the input choices are chosen with a different distribution, but for the purpose of the improvement in this work, we find that the uniform distribution appears to be optimal. Now, of course, you might ask, what is the point of considering a situation where you pick the basis choices uniformly? Because after you include the sifting factor, it seems that surely the key rate would be lower than the situation where you mostly use just one basis pair for key generation. And the reason why we are interested in considering this is that for DIQKD, the known noise tolerances for the known protocols are fairly low. So right now, we are only interested in looking for a situation where the key rate is positive. So we don't really worry about whether the key rate is low. We're just interested for now in whether the key rate for a given implementation is a positive value. In that case, we can essentially ignore the proportionality factors and we just look at expressions which the key rates are proportional to, which we show on the right of the screen here. In the expressions on the right, I've also somewhat simplified the formulas by assuming that the noise model is depolarizing noise. In that case, the terms involving Bob simplify to just the binary entropy of the QUBA. And that means that in the bottom box here, I've essentially ignored the sifting factor because we are just interested in whether this expression is positive. And in that case, it comes down to comparing the expressions in the highlighted boxes over here. On the top, we have essentially the conditional entropy of just Alice's measurement A0 against Eve. And on the bottom, we have essentially the average conditional entropy of A0 and A1 against Eve. And this brings us to the key insight of this work, which is that if you consider devices that produce a given amount of CHSH violation, then in general, the worst case value of the A0 conditional entropy is going to be smaller than the worst case value of the average conditional entropies of A0 and A1. Of course, you might ask, why should we expect this to be the case? And there is certain intuition that can be found behind why this inequality is often a strict inequality. This is because for the CHSH protocol, we have to allow, if we consider the expression just on the left, we have to allow the A0 measurement to be essentially the worst case measurement in the sense that it leaks the maximum amount of information to Eve. But the CHSH inequality has a very important property that if there is any non-trivial violation, if the CHSH value is larger than 2, then the A0 and A1 measurements cannot be the same measurement. And because of this, we can conclude that in particular, they cannot both be the worst case measurement. And because of this, we can expect that the right-hand side of this inequality here will quite often be strictly larger than the left-hand side. And this is the key insight that leads to the improvement in this work. As a quick note, I should mention that for other protocols such as the BB84 and the 6-state protocols, we cannot expect an improvement using this approach. In some sense, these protocols have too much symmetry, and it's actually possible for both A0 and A1 to be both the worst case measurement in some sense. And this means that using the protocol we consider here with the uniform basis choice, what we are interested in is finding the worst case value of this average of entropies of A0 and A1. And the only thing we know is that the devices are performing states and measurements such that the CHSH value is the observed value. It's perhaps not completely obvious why Bob's measurements are involved here because they don't appear in the objective function, but in fact they appear in the constraint because they are responsible for determining what CHSH value is observed. At first, this might seem like a pretty challenging problem to solve because you are doing an optimization over the states and the measurements. Plus, in addition, we do not know even the dimensions of the systems. But since for this work we focus on the CHSH inequality, which has only 2 inputs and 2 outputs, we can use a result sometimes known as Jordan's lemma, which essentially reduces the analysis to qubit states. So the dimension is bounded, apart from a small technicality about taking convex mixtures at the end of the argument. And I'll now briefly describe how we tackled this optimization problem. Essentially, the approach we used was to address the optimizations over Alice's measurements, Bob's measurements, and the shared state one at a time. So first of all, the optimization over Alice's measurements was tackled in a fairly direct fashion. We just used a continuity bound in the sense that if Alice's measurement changes by some small epsilon, we proved that the objective function and the constraints can only change by some small function of epsilon. And this means that in principle, we could solve the optimization over Alice's measurements just by computing the values over a grid of points, a grid of possible values for her measurement, and then taking the worst case, because the continuity bound assures us that the true minimum cannot be more than a small value less than the minimum on this grid. In practice, we found that it was somewhat more efficient to use an iterative process where we only make the grid finer in the points that are close to the true minimum, although I will not go into detail on this here. As for the optimization over Bob's measurements, in principle, we could also do it using a continuity bound approach. But for this work specifically, we instead used another approach that was used in a previous work, where essentially we relaxed this optimization to a sequence of approximations that converge to the true value. Although, importantly, we make sure that at each approximation, the bound that it yields on the entropy is a secure lower bound, so we never overestimate the key rate. I won't go into details on the approach here, but as a very quick summary, the idea is to observe that the optimization domain can essentially be parameterized as a semicircular arc, and we relax the optimization domain to a polygonal approximation. Then we iteratively refine this polygonal approximation by slicing off pieces from it until it eventually converges to the true minimum. And lastly, to tackle the optimization over the states, what we did first was to use an observation that has been applied in standard QKD in several works. Basically, this is a relation between the conditional entropy of the measurement against Eve and a relative entropy expression that only involves the Alice-Bob state. So this is quite convenient because it reduces the entropy expression to something that only involves the honest parties. What we do next is to apply an inequality that we derived for this work, which is something like a Pinsker inequality in the sense that it gives a lower bound on the relative entropy in terms of a trace distance. After simplifying the expression a little bit more using a convexity argument, we see that essentially in order to lower bound the average of the conditional entropies on the left, what it comes down to is to bound this trace distance expression here. But the trace distance is convenient because it's in fact possible to compute it using a semi-definite program. And this is the approach that we used in order to solve the optimization over the states using semi-definite programming. So that was a very quick summary of the approach that we used in order to compute the key rates. But now I'd like to turn to the results that we obtained in terms of the actual key rate values that we got. So in this graph here, the gray curve essentially shows the results for the uniform basis choice that we are studying. And the blue curve here shows the key rates for the standard protocol. The purple dots along these curves are basically the maximum of the two curves. We see that in the regime of high CHSH values, in other words, when there's not much noise, well, the standard protocol outperforms the uniform basis choice protocol, and this is because of the sifting factor. So we lose a factor of essentially half because of sifting out about half of the rounds. But the important point for this work is that if we study instead where the key rate reaches 0, we see that the uniform basis choice protocol is much more robust against noise because it achieves a non-zero key rate up to this point on the graph here. Whereas if we compare it to the standard protocol only has a non-zero key rate up to this point. As a small additional note, this if we plot the graph of the bound on the entropy function alone, then it turns out that our bound is almost the best possible bound that you could expect in this situation. Because we see from this graph that the plot of our results on the purple dots here is almost a linear interpolation between the endpoints. And by using a strategy mixing argument for Eve, it can be shown that the true bound on the entropy can at most be the linear interpolation between these 2 points. So our bound is in fact close to the best possible for this situation. Although I should specify that the graphs shown on this slide, they are for the situation where the form of noise under consideration is just depolarizing noise. So white noise, or you could also think of it in terms of measurements on a Werner state. If instead we want to consider a different noise model, for instance, if we want to consider photonic models, then the situation becomes more complicated. You can see from the plot of the key rates here that even though our results do provide some improvement over the standard protocol, which is again shown in blue, especially in the regime of lower detector efficiencies, the threshold of the two protocols is still approximately the same value, more or less. So for photonic models, it seems like our approach does provide some improvement to the key rate, but it doesn't seem to change the threshold efficiency at which a positive key rate is achieved. In order to see why this might be happening, we have to go back and look at the original expression for the key rate when you have uniform basis choices. Basically, the two terms in the box here involving the conditional entropies versus Bob, for the photonic model, these two terms tend to have somewhat different values, and it seems difficult to choose experimental parameters such that both of these values are small at the same time. So somehow this seems to be posing a difficulty in applying our approach for photonic experiments. And having covered some of the basic noise models, I shall describe now the implications of these results for the existing bell test experiments. On this graph here, we have essentially plotted a region plot of our results where the two axes are the QBer as well as the CHSH value. The blue region here is the region of positive key rates from the uniform basis choice protocol, and the darker blue regions correspond to higher key rates. On the right of this slide, we have a very similar plot that was developed for the standard protocol. This was from a previously published work, although in that work they used green to denote the areas of positive key rate. And on both of these graphs, the small points with the corresponding error bars are essentially the CHSH and qubit values achieved in a number of Bell test experiments, which are listed on the right here. Although for now, I want to draw your attention to these loophole-free Bell tests, because out of this list, these are the Bell tests that are loophole-free. So focusing only on these loophole-free Bell tests, we see that there are a few on these graphs that have essentially achieved positive asymptotic key rate. On the right-hand side, we see that experiment number 7, which is essentially the NV center Bell test, is just barely on the edge of achieving a positive asymptotic key rate using the standard protocol. But with our results on the left-hand side, we see that this experiment, number 7, has achieved a strictly positive key rate. So there is some improvement here. We also find that another experiment using cold atoms was also able to achieve a positive asymptotic key rate if we consider using our protocol on it. So from this slide, we can see that in fact, some of the existing Bell test experiments can now be considered to have the capability to achieve a positive asymptotic key rate for QKD. But of course, the natural question here is whether the key rate is still positive after we take finite size effects into account. And this is important because the different experimental implementations have extremely different sample sizes. In particular, the photonic experiments tend to have much larger sample sizes than the NV center and cold atom experiments. So in order for there to be a fair comparison, we should probably do a finite size analysis as well. But before moving on to that, I also want to briefly mention that for photonic experiments, there is a different approach that may turn out to be more promising. And this was put up on arXiv only a few months ago and also published. So the approach is to use a trick from standard QKD known as noisy preprocessing, which can substantially improve the noise robustness for standard QKD. And in this work, we show that it also improves the robustness of DIQKD. In particular, we find that by applying noisy preprocessing, the threshold detector efficiency you need in order for the asymptotic key rate to be positive can be reduced to about 83%, which is apparently roughly within the range of existing Bell test experiments that are based on photonic implementations. So from this perspective, it seems that the photonic Bell test experiments may also be able to achieve a positive asymptotic key rate by making use of this noisy preprocessing result. We will be presenting this result as a poster in the upcoming sessions, so we will be glad to take any questions you have during that poster session as well. So as mentioned, one of the key questions that we now need to address regarding this work is to conduct the finite size analysis in order to have a more reasonable comparison between the different Bell test implementations. We currently have this in preparation and we are now writing up the results. Another point that we are actively working on is how to incorporate noisy preprocessing into this approach using the uniform basis choices. The approach that we are currently using to study this also has the advantage of being a slight improvement in the optimization process over the states. And the current numerical indications we have from this is that if we look at the depolarizing noise situation, the threshold can be improved up to about 8.9%, roughly speaking. Other benefits of this approach include the fact that it allows you to impose multiple constraints instead of just one inequality, such as the CHSH inequality, and it will also tell you a single Bell inequality that certifies the same entropy as the multiple constraints. In the theoretical aspect, this approach also has the benefit that it yields affine bounds on the conditional entropies. So this is useful for the finite size analysis if we are going to do it based on the entropy accumulation theorem. Finally, one very important point to consider is as well how to optimize the experimental implementation. This is a little bit tricky because there are a large number of experimental parameters and options to consider, but we have some ideas that we are currently exploring. Finally, I would like to briefly describe some other generalizations of our work that may also be of interest. So one point to consider is what happens if we want to do protocols that have more inputs and outputs, so we no longer have the reduction to qubits. In that case, one approach that could be applied is a technique that was described in a previous work of ours from last year, which uses a sequence of semi-definite programs known as the NPA hierarchy to bound the entropy without using a qubit reduction. We did try applying it in this situation, and we verified that it also certifies there is some improvement over the standard protocol using uniform basis choices, but the improvement that we get using this technique, that we can prove using this technique, is less than the graphs that we have shown here. Another approach that might work is to consider the modified Pinsker inequality that we have described in this work. In fact, this was one of the original motivations for the development of this Pinsker type inequality, because in fact, even without the qubit reduction, you can bound the trace distance expression here using the NPA hierarchy of semi-definite programs. And it turns out when we tried using this approach that when there is no noise, this approach can actually certify tight bounds on the entropy. And the benefit of it is that it is much faster than the approach in the previous paper. However, the drawback of this approach is that it doesn't seem to be very robust once we start adding noise. So we are still looking into whether this technique can be improved further. Finally, there is one conjecture that we have been thinking about for a while, but have not managed to prove yet. And the idea is essentially this: there is an inequality that relates the conditional entropy and the fidelity of Eve's conditional states. So this is already a known result, but if we make the further assumption that Eve's states are pure, her conditional states specifically, then we can actually write an exact relation between the fidelity and the trace distance. Basically, this means that the Fuchs-Van de Graaff inequality is actually saturated. The reason why this is useful is that the trace distance can again be bounded using the NPA hierarchy, and this approach is much more efficient than the SDPs we have previously described. When we have tried experimenting with this approach under the assumption that this conjecture is true, we find that the results seem to match to numerical precision to the results that we obtained by other means. So it seems likely that this conjecture is true, but we need to be able to justify it. So the second line, this equality here, we are curious about how to prove that it might be true. For instance, one way to do it would be to argue that Eve's conditional states are indeed pure, but in this direction, it turns out that there are some situations where the equality holds even if the states are not pure, and perhaps it might be of interest to find out what are these situations as well. To sum up, in this work, we have described a protocol that substantially improves the noise tolerance of DIQKD by choosing the basis choices uniformly at random instead of mostly generating the key from one measurement pair. Going forward, we are writing up our results regarding the finite size analysis of this protocol, as well as an improved optimization method that takes noisy preprocessing into account. We are of course very hopeful that this will lead to a finite size implementation of DIQKD, and we are having discussions to see what experimental implementations might be possible. In addition, in just the past few weeks, there have been a number of papers on computing the asymptotic key rate for DIQKD, and it would of course be interesting to compare the results in this work to the results that they have obtained. I thank you for your time, and I'll now be glad to take any questions you might have.